right, let's go look at the slides for chapter 20, inference about a population mean. In chapter 20, we cover conditions for inference about a mean, the t-distributions, the one sample t-confidence interval, the one sample t-test, using technology, matched pairs t-procedures, robustness of t-procedures, resampling and standard errors. Conditions for inference about a mean. Here are the conditions needed for realistic inference about the population mean. Conditions for inference about a mean. We can regard our data as a simple random sample, SRS, from the population. This condition is very important. Observations from the population have a normal distribution with mean mu and standard deviation sigma. In practice, it is enough that the distribution be symmetric and single-peaked unless the sample is very small. Both mu and sigma are unknown parameters. First, a caution about mean. A condition that applies to all the inference methods in this book, the population must be much larger than the sample, says at least 20 times as large. Previously, we assumed that we knew the population standard, sigma, and thus were able to compute probabilities for a sample mean. In practice, we do not know sigma because we don't know sigma, we estimate it by the sample standard deviation S. We then estimate the standard deviation of x bar by S divided by root n. This quantity is called the standard error of the sample mean x bar. Standard error. When the sample standard deviation of a statistic is estimated from data, the result is called the standard error of the statistic. The standard error of the sample mean x bar is S divided by root n. The t-distributions. When the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing it. So z equals x bar minus mu divided by sigma divided by root n. We don't know sigma. We estimate it by the sample standard deviation S. What happens when we standardize? So here we have an image of our x bar values where we have a standard deviation sigma over root n and a sampling distribution of x bar. So the new curve doesn't have a standard deviation. It doesn't have a normal distribution. The slides are kind of weird. So we can't use z is what they're trying to get at. We're going to be using what we call t, because the difference between the above z is there's sigma in the bottom, and the one on the bottom of the screen has s instead of sigma. The t distributions. When we standardize based on the sample standard deviation S, our statistic has a new distribution called a t-distribution. It has a different shape than the normal curve. It is symmetric with a peak at 0 However, it has much more area in the tails. The t statistic has the same interpretation as any standardized statistic. It says how far x bar is away from its mean mu in standard deviation units. There is a different t distribution for each sample size specified by its degrees of freedom. When we perform inference about a population mean mu using a t distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n, making the df equal to n minus 1. We will write the t distribution with n minus 1 degrees of freedom as t parentheses n minus 1. It is symmetric with the single peak at 0. However, it has much more area in the tails. Oh shoot, did I go backward? Oh no, it's just a repeat of what we had before. The one sample t statistic and the t distributions. Draw an SRS of size n from a large population that has the normal distribution with mean mu and standard deviation sigma. The one sample t statistic is then t equals x bar minus mu divided by s divided by root n, which has the t distribution with n minus 1 degrees of freedom. When comparing the density curves of the standard normal distribution and the t distributions, several facts are apparent. The density curve of the t distributions are similar in shape to the standard normal curve. They are symmetric, about 0, single peaked, and bell-shaped. The variability of the t distributions is a bit greater than that of the standard normal distribution. The t distributions in figure 20.1 have more probability in the tails and less in the center than does the standard normal curve. This is true because substituting the estimate S for the fixed parameter sigma introduces more variation into the statistic. As the degrees of freedom increases, the t density curve approaches the normal with mu equals 0, standard deviation 1 curve, the standard normal curve, ever more closely. This happens because S estimates sigma more accurately as the sample size increases. So using S in place of sigma causes little extra variation when the sample is large. When we use table C in the back of the book to determine critical values T star for T distributions with different degrees of freedom. Using table C, suppose you want to construct a 95% confidence interval for the mean mu of a normal population based on an SRS of size n equals 12. What critical T star should you use? The upper tail probability P. Our degrees of freedom is a column listed on the left-hand side. And across the top, we have confidence levels, C. In table B, we consult the row corresponding to the degree of freedom, n equals n minus 1, which equals 11. We move across the row at the entry that is directly above the 95% confidence level. The desired T star is 2.201. One sample t confidence interval. The one sample t interval for a population mean is similar in both reasoning and computational detail in one sample z interval for a population proportion. The one sample t confidence interval. Draw an SRS of size n from a large population with unknown mean mu. A level confidence C, confidence interval for mu, is x bar plus or minus t star times s divided by root n, where t star is the critical value for the t parentheses n minus 1 density curve with an area C between minus t star and t star. This interval is exact when the population distribution is normal and is approximately correct for a large n in other cases. Example, does the expectation of good weather lead to more generous behavior? Psychologists studied the size of the tip in a restaurant when a message indicated that the next day's weather would be good was written on the bill. Here are tips from 20 patrons measured in percent of the total bill. We want to estimate the mean tip for comparison with tips under the other conditions. Plan. We will estimate the mean percentage tip mu for all patrons of this restaurant when they receive a message on their bill indicating that the next day's weather will be good by giving a 95% confidence interval. Solve. Checking the conditions. The SRS. The study was actually a randomized comparative experiment. As a consequence, we are willing to regard these patrons as an SRS. Normal distributions. We can't look at the population, but we can examine the sample. The stem plot does not suggest any strong departures from normality. The sample size is at least 15, so we are comfortable using the t interval. We can proceed to calculation. For these data, x bar equals 22.21 and s equals 1.963. So the mean of this sample and the standard deviation of this sample. The degrees of freedom are n minus 1, which is 19. From table C, we find that the confidence interval, we find that for the 95% confidence, T star equals 2.093. The confidence interval is x bar plus or minus T star times S divided by root n, which equals eventually 22.21 plus or minus 0.92, or 21.29 to 23.23%. Conclude. We are 95% confident that the mean percent tip for all patrons of this restaurant when their bill contains a message that the next day's weather will be good is between 21.29 and 23.13%. The one sample t-test. Testing hypotheses about mean mu, of a normal population follows the same reasoning as the testing hypotheses for a population proportion that we met earlier. The one sample t-test. Draw an SRS of size n from a large population having unknown mean mu to test the hypotheses that H naught is U equals mu naught. Compute the one sample t statistic T equals x bar minus mu naught divided by S, which itself is divided by root n. In terms of the variable t having the t parentheses n minus 1 distribution, the p-value for a test of h naught against either mu greater than mu naught, mu less than mu naught, or mu not equal to mu naught for the alternate hypothesis. If mu is greater than mu naught, then p is the probability that your t test statistic is greater than, that a t is greater than your t statistic. An alternate hypothesis that mu is less than mu naught has a p value of the probability that t is less than your t statistic. And an alternate hypothesis that mu is not equal to mu naught has a p-value of 2 times the probability that a t-score is greater than the magnitude of your t-score. These p-values are exact if the population distribution is normal and are approximately correct for large n in other cases. Example, we follow the 4-step procedure for a significance test. State the problem. Ohio considers it unsafe if a 100 milliliter sample, about 3.3 ounces of water, contains more than 400 coliform bacteria. Here are the fecal coliform levels found by laboratories at 20 Ohio State Park swimming areas. 160, 40, 2,800. Ugh. Are these data good evidence that on average the fecal coliform levels in these swimming areas were unsafe? Plan. We asked the question in terms of the mean fecal coliform level, mu, for all these swimming areas. The null hypothesis is that the level is not unsafe. The alternative hypothesis is level is unsafe. So the unsafe level was more than 400. So the null hypothesis is mu equals 400. The alternative hypothesis is that mu is greater than 400, therefore not safe. All right, we are willing to regard these procedures, we are willing to regard this particular 20 samples as an SRS from a large population of possible samples. The histogram of 20 samples doesn't let us judge normality, but the data are somewhat skewed. The sample size is larger than 15, so it is safe to use the one sample t-test, but p-values may be off. Based on x bar equals 1,231.3 and s equals 1,037.5, the one sample t statistic is t equals x bar minus mu naught divided by the quantity s divided by root n, which equals 3.583. The p-value for t is 3.583. Is the area to the right of 3.583 under the t distribution curve with degrees of freedom n minus 1 equals 19. We will show the calculation of the p-value and the resulting conclusion in the using technology section next. Using technology with confidence intervals. So in your calculators, you have a T interval. You have the TI 83 plus, the mini tab, or the Excel. Excel is usually my favorite. Crunch it. Comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals result in paired data. When paired data result from measuring the same quantitative variable twice, as in job satisfaction study, we can make comparisons by analyzing the differences in each pair. If the conditions for inference are met, we can use one sample T procedures to perform inference about the mean difference. Matched pairs T procedures. To compare the responses to the two treatments in a matched pairs design, find the difference between the responses within each pair. Then apply the one sample T procedures to these differences. Robustness of the T procedure. A confidence interval or significance test is called robust if the confidence level or p-value does not change very much when the conditions for use of the procedure are violated. Using the T procedures, except in the case of small samples, the conditions that the data are an SRS from the population of interest is more important than the condition that the population distribution is normal. Sample size less than 15. Use T procedures if the data appears close to normal. Roughly symmetric, single peak, no outliers. If the data are clearly skewed or if outliers are present, do not use T. Sample size at least 15, so 15 and larger. The T procedure can be used except in the presence of outliers or strong skewedness. For large samples, the T procedure can be used even for clearly skewed distributions when the sample is large, which here roughly means greater than 40, greater than or equal to 40. Resampling and standard errors. Previously, we defined the standard error of a statistic to be an estimate of the standard deviation of the statistic. For the sample mean X bar, the standard deviation is sigma divided by root n. A natural estimate is S divided by root n, which is commonly referred to as the standard error of X bar in textbooks and computer output. We can also use resampling methods to estimate the standard deviation of many sample statistics, such as the sample mean or sample median. The basic idea is to take many SRSs from a population, compute the sample statistic for each, and then compute the standard deviation of these values. This is an estimate of the standard deviation of the sample statistic, sometimes referred to as the resampling estimate of the standard error. Remember, the standard deviation of a sample statistic is the standard error. The sample deviation of a sample statistic is the standard error. There's no need to divide the standard deviation of a sample statistic by root n. In practice, we typically do not know the exact distribution of the population. For example, as is the case in this chapter, we may know the population is approximately normal, but not know the mean mu, the standard deviation sigma. For purposes of resampling, in such cases, we estimate these unknown features of the population distribution from data.